Hey, this is Don from Padlock Technologies again with another video. This time we're going to take a little deep dive into MPLS TE using RSVP as the label signaling protocol. Now, if you don't know anything about MPLS, I did a brief MPLS fundamentals video. I'm going to put it up here so you can watch that, and then you can come back to this video because you're going to now see what RSVP looks like. Now, I do have a favor from you. If you do find value from this video, please don't forget to share, comment, like, and subscribe. Tell a friend to tell a friend. My channel is growing, and you're going to do somebody a great favor because if they're struggling with RSVP and they want to learn it, they can watch this video. With that being said, let's get in the lab. All right, so here's the lab. Now, I may have did some stuff on this before, but you never know. So I just recreated it. So let me tell you what's going on here. Basic lab, we're running MPLS, we're running VPN-v4, so we're doing IPv4, and we're running ISIS as the IGP, the underlay. Again, OSPF or ISIS, you need these protocols to do RSVP or MPLS TE because it's a link state protocol. You can't do this with EIGRP or, God forbid, RIP or anything like that. If you got RIP in a service provider network, you need to be examined. Like, seriously. If you're even using RIP in today's network protocols, you need to be examined. I'm telling you that right now. So what we got here is I do have some VPLS going on. So from router 3 and 12, we have VPLS going on there, but routers 15 and 9 are running regular peering MPLS L3 VPNs. I have PE1 and PE2 basically doing MPBGP. I always get tongue tied with that. And they're running VPN-v4 and the VPLS AFI sub AFI. You don't know anything I'm talking about, don't worry, keep studying. It'll make more sense once you start reading some books. Like I said before, AFI, address family identifier, sub AFI, which is, the secondary AFI that you're going to be triggering. So for this, case in point, this is going to be VPN-v4 as the AFI, unicast is the sub AFI. Okay? And then L2 VPN, VPLS. So L2 VPN is the AFI, sub AFI is VPLS. Okay? So with this being said, I am going to purposely, this is the traffic engineering part. I'm going to send my traffic for the peering VPN from router 1 to router 4 to router 7 to router 2. Why? Because I'm using this thing called an explicit path. So let's go into router 4 so I can give you the basic constructs on how to get MPLS TE working. And then we'll talk about the explicit path stuff. And I also have some MPLS TE FRR. So I have a backup LSP. And we're going to simulate that by shutting down this interface G2. And we're going to watch the LSP, the backup LSP get triggered and still get to the merge point. So let's get into the basics here. So router 1, router 2, they are the head end, tail end, okay? Depending on the direction you're looking at. So from 1 to 2, 1 is the head end, 2 is the tail end. From 2 to 1, 2 is the head end, 1 is the tail end, okay? These are the mid routers, okay? So what we're going to do is we're going to build a tunnel from 1 to 2, and we're going to force it to go wherever we want. But before we do all that, let's get into router 4 here, so we can talk about some of the basic constructs of MPLS TE. So first things first, you have to turn on the feature. To do that, you need to use a command called MPLS Traffic Engineering Tunnels. So I do show run section MPLS. This is the command right here you need to turn on. That's the first thing you need to do. Turn on Traffic Engineering Tunnels. Okay. The second thing you need to do is you need to do two things on the interface. You need to reserve the bandwidth that you're going to allow RSVP to use, and you need to actually put the command MPLS Traffic Engineering Tunnels on that interface as well. If you do not do this, MPLS TE will not work, right? And as I was doing this, it's been a long time since I did it. I forgot to do that, and I was like, why are my traffic engineering tunnels not working? And it was because I forgot to put MPLS Traffic Engineering TE or Traffic Engineering Tunnels on the interface. So if we look at G4, what we're looking at here is this command, all right? and then I'm saying I'm going to use 50% of the bandwidth or the total bandwidth on the link. So this will allow RSVP to, reserve bandwidth when I use my constraint. Now, once that's all done, you're going to go under your ISIS protocol or OSPF if you're using that, and then you're going to activate MPLS TE by using the MPLS Traffic Engineering Router ID loopback. And then you're going to say this is going to be for level 2 because all the routers in this deployment are level 2 routers. They're not level 1 routers. So if I go to ISS, these are the commands you're looking at here, and you also have to do metric style wide, okay? Because that's going to allow you to actually do MPLS traffic engineering. If you use the normal metric style, the narrow metric, it will not work. So you can't do that. All right, you definitely, now the metric style wide is not a command under OSPF, so that's not a command that you have to put there, but you do have to put these commands. So in OSPF, instead of saying level 2, it'd be area 0 if you're going to do this with area 0. But you normally definitely have to have these two commands in there from a routing process standpoint. Okay. Once that's done, you're pretty much set up for MPLS TE from the mid router side. Now, when we get to the head end and tail end, a lot more configurations from the tunnel standpoint, and I'll explain that as well. Now, what does this do when you put MPLS TE here? So the first thing we're going to do is we're going to, like I said in the other video, there is no LDP in this setup whatsoever. So if I go show MPLS LDP neighbor, you see there's no LDP neighbor because I'm not using LDP. So this tells you that you don't have to use just LDP for label signaling. And if you looked at the last video, I told you it's LDP, RSVP, BGP, segment routing. Those are the 4 things you can do. And I know I have my pinky twitching here. Those are the 4 things you can do to signal labels. It's not just LDP, but when you're going for your CCIE enterprise, you are going to be indoctrinated, which is LDP. So just know the world's bigger than LDP. All right. So now, if we go to our show MPLS forwarding table, we still got labels here. And what you will see is a T next to it because this is the tunneling mechanism, right? This is the tunneling. You see it says point to point there. Okay. So what you're going to see when we do FRR or router 4, yeah, I'm on router 4. When you see FRR, what's going to happen is there is a backup tunnel on this router itself. So it's going to go, hey, when I break this link, use this other LSP to get to the midpoint. So I'll explain that a little bit later. So I'll actually explain it now. The midpoint is router 7, and you'll see that when we look at router 1, when I direct traffic to where it needs to go, router 7 is technically the midpoint. So what's going to happen is when the FRR kicks in, if this link 2 goes down, my backup LSP goes to from router 4. I don't know why that just happened. It goes from router 4 to router 5 to router 7. So 7 is still the midpoint. The primary path is router 1, 4, 7, 2. Backup goes 1, 4, 5, 7. So as you can see, I said 7 twice. So that tells you that 7 is the midpoint. This is what you call link protection, right? So there's 2 types of protections in MPLS TE. There's link and there's node protection. Link protection is next hop. They call it next hop, FR, next hop, whatever you want to call it. And then if I did node protection, this is if this entire router went down, I have another way to get there. They call that next hop, next hop. And then MPLS TE world, next hop is more preferred than next hop. Okay? Because you're factoring the link and the node. So if that node goes down, all the links are down. You have to find another way to get there. So you have to already have these paths pre-built in the network. So if something happens at the data plane, it switches right over. Think of it like normal network conversion when you're using like BFD. People think, oh, just put BFD on there and you're fine. BFD is a failure mechanism, right? It speeds up failure detection. It does not help you in terms of data plane, in terms of do I have a pre-built backup path in my routing table already? This is where you have to do things like loop-free alternates, right? And then the loop-free alternate world, there's regular LFA, there's remote LFA, and then there's TI LFA, which is topology independent LFA, which you can only do with something called segment routing, okay? I know I'm rattling a lot off to you, but this is the stuff that you need to know from a design standpoint when you're like helping out people build designs and stuff. You got to know, okay, well, if we're not using segment routing, we can't do TI LFA, which would give you like 100% coverage. We can only do either normal LFA, which gives you some coverage, or remote LFA, which gives you more coverage than normal LFA because you're running the algorithm from a remote node. Okay, so you'll understand that. Run this video back, listen to it again, then read MPLS fundamentals and read MPLS fundamentals really, and then it'll make all more sense. So let's talk about the backup. I'll go back to router 1 to show you the actual path, and then we'll go back to router 4 so I can show you the backup LSP. So on router 1, we have two things here I want to show you. So if I show you show run section IP, I'll just do that. So we have this thing called an explicit path. Now, when you do MPLS TE, there's two ways you can do this. You can do dynamic path option, or you can do an explicit path option. Dynamic path option is going to take the calculations from the IGP and find the best path to the tail end, right? Because this is still PE to PE transport. This has nothing to do with customer traffic per se. This is just how do I get to the access points. So this explicit path basically says, now I called it router 1, router 4, router 7, router 2, but if you look at the next address, it's only 4, 7, and 2, right? I just put router 1 in there to tell you where the heading is. So this is going to tell you that if I use this option in my traffic engineering tunnel, it's going to go to router 4, router 7, and router 2. And then it's going to go pop out the other end. And there's going to be labels in that path. So once I establish the tunnel, remember what I said in the other video, router 1 is going to send a path message all the way through the network to get to router 2. And then if it matches my constraints, I'm going to get a reserve message back. And as the reserve message is going back, labeling is now happening. A label is now being created. Okay, so the one thing you need to understand about MPLS TE is the reason why you can use constraints is called CSFP, which is constraint SFP. There's different versions of the SFP algorithm. There's normal SFP or SPS. I don't know why I keep saying SFP. SPF, and then there's CSPF, which is constraint SPF. Then there's ISPF, which is incremental, which is, hey, if there's a break somewhere in the area, it only runs the algorithm again on the break and not the entire area. It's all kind of stuff, man. And then there's reverse SPF, which is running the algorithm from a different router in the network, right? And then they're the root of the tree, and then you can run your calculations from there. You see that in something called optimal route reflection. I did a video on that. I'm gonna put that up here as well. Go check that out. That's a really cool technology for running, for getting different points of references. So different routers are going to pick different points based on them being the root and not from the route reflector's point of view. So it's very cool. Watch that video. Back to this. So I'm going to use this explicit path in my tunnel creation to say this is where you're going to go. Okay, this is how traffic's going to get from head end to tail end. Now router 4 has a backup LSP that says if link 2 goes down, I'm going to go from, instead of going to 4 directly to 7, I'm going to go to 5, then I'm going to go to 7, then 1 to 2. Okay, so let's look at what that tunnel looks like actually. So if we go to show run tunnel 0, this is the traffic engineering tunnel in a nutshell. Now, BGP is still working, MPBGP, VPN v4, VPLS, that's already set up. But this is the main piece. So usually when you create these tunnels, you're going to copy the IP address from the loopback. That's fine. Then you need to put it in, tunnel mode here. Then you have to I usually do this destination last before I set all this up. All right, so the auto announce, this puts the tunnel in the routing table automatically as soon as it's established. If this is not, if you don't have this command, then you're going to have to use something like PBR, which I'm probably going to create another tunnel based on that and show you PBR in another video. But if this is not there, it does not put the tunnel in the routing table. So the tunnel's up, but to get to router 2, it'll just take the normal path, right? And when you auto announce it, then you'll see the tunnel as the destination, or the tunnel as the next interface or the next hop. Now this priority, this is automatically put in there. This is like hold values and stuff like that. This is if you have multiple tunnels, you get to have preference of which tunnel is more, important than the other one, but that's automatically created if you don't actually adjust that. Then you have the bandwidth one. This is my constraint. So I'm basically saying, hey, find me a path that's, at least one, I think it's kilobits per second, at least 1 kilobits per second, right? And as long as that path is available, it will generate, the whole link label switch path. This is me telling it where to go, which is, like I said, the path option, which is saying, hey, you're going to go with this explicit path here. So you're going to go to 4, 7, and 2 as to get to the tail end. This metric is path selection. Now there is 2 things you can use. You can use the IGP or you can use TE values, but you have to manually make those TE values on the link. So that's why people don't really use TE. You can also do affinity attributes and stuff like that all over the network and say, hey, I only want this tunnel to take the path for this with this specific affinity value in my network, and then it will find it, and that's the path it will go. But that's way too complicated for this video. I may, if you want to show you video on affinity values and stuff like that, put it in the comments, and I'll I'll create a video using the same lab on that. And then this command here is the FRR from the headend. See, the FRR is not initiated by router 4. I just create the backup LSP. Until the headend says, hey, I want to use fast reroute, that backup LSP is useless, right? As soon as I put this command in and I tell the link interface that, hey, you're going to use that backup tunnel, now FRR is in play, okay? So the magic of all of this and why you have to use a link state protocol again is because the link state protocol carries a lot of information that CSPF is going to use to make its routing decisions. What does that database look like? So we go show MPLS Traffic Engineering Database. Is it database? Oh, is it topology? I think it is. There we go. So if we look at our topology here, you can see all of the stuff that is carried in the LSA. So these are LSA 10s, opaque LSAs. Okay. So remember, if we're going to go down the path of LSAs for OSPF, you got your router LSA, you got your network LSA, you got your network summary LSA, you got your ASBR LSA, you have your external LSA, you have a group membership LSA. Rarely does anybody know about LSA number 6 because it's not really used, but it's a group membership. Then you have your router 7, which is your what? External LSA coming from an NSSA, right, from a not so stubby area. Then you have your 8, which is, I think, is inter prefix. Don't quote me on that, but that's for IPv6. Then you got your inter prefix, which is IPv6, which is 9. And then you have 10, which is your opaque LSA, which is for traffic engineering. So the stuff you've seen in here is LSA 10. This is all the stuff that you would see. But as you can see, you get all this data in the opaque LSAs, right? And this is what the CSPF uses to make decisions, or to say, hey, you told me you want to look for a path that has at least 1 kilobit per second. Okay, I'm going to look at my database and find that path. I know everything in this area because we share the same database, so I can easily look at everything and I can find you that path with that constraint. But this is what it's doing behind the scenes. It's looking at this topology information to find that information. So next, now that the tunnel is up, now we use another command called show MPLS Traffic Engineering. Come on, Traffic Engineering Tunnels. And as you can see, my tunnel, the path is valid, right? Let me give you a lot more information here. So here's the tunnel. Path is valid. That means CSPF was able to find a path based on that constraint. It's using this explicit path that I told it to go. And then if you look down here, you'll see the next hop. That's the label is 18. Tells you my next hop is this link right here. Right? Told you the signal information. Here's the explicit path right here. So when I do the trace route, we should see it go from it should go from G1 link, and then G2 link, and then G4 link. That's based on this path here, and then obviously it gets to router 2. All right. And then all that, we got the fast reroute path verification. I think that failed because it's not technically, I didn't bring down the link, so you're not going to see that. And that's it. That's the tunnel information. So now let's go to router 4 again, and I'll show you the backup LSP. So now the backup LSP is, we're going to first go to that interface there. And as you can see, I'm using this command here, MPLS Traffic Engineering Backup Path Tunnel 0. So that is saying, hey, this link is going to use tunnel 0 if it goes down. So the backup path, if this link goes down, is tunnel 0. So if we look at tunnel 0, as you can see, this is tunnel 0. Now, what is the difference here? A couple things are different in router 1. One, I think I got a command in there that shouldn't be really in router 1, which is MPLS Traffic Engineering Tunnels, because you don't know, you're not going to do that on the tunnel interface. I don't know how that got in there. It must have been just typing too fast and forgot. But that's irrelevant. The key thing here is auto route announce is not here. You don't see it, right? Everything else is the same, but you don't see auto route announce. That means that it is not in the tunnel, right? It's not automatically in the routing table. So if we look at the routing table here, to get to tunnel 7, to get to router 7, as you can see, you don't see tunnel, right? So if I go back to router 1, if I go show IP routes, see that? To get to router 2, you see how it says tunnel 0? That's because I use the auto route announce command. So it's going to go take that LSP going through tunnel 0. Normally, it would just use IGP like router 4 is using. Okay? So right now, if I go, same thing here, show MPLS Traffic Engineering Tunnels, we have a tunnel, it's valid, is using that same path. Now I'm going to show you something else. If I go show IP RSVP, I think it's fast reroute, there it is. Fast reroute, there you go. So what this is saying is I have a backup tunnel to router 7. The label is 17. It's in ready state, and the type is a next hop. Okay, it's a next hop because I'm doing it on this link here. I'm not doing next hop. I'm just doing next hop. So again, router 7 is the merge point. So even if this 2 goes down, I'm still going through router 7 because I'm simulating that router 7 link is down, not router 7 is down. Okay. So the main thing I want you to pay attention to is this label 17. So when we look at the initial label switch path, you're not going to see 17. You'll see 16 coming from router 7. If we go to router 7, we look at the forwarding table, we got a 17 here. Now what happens is when we look at the trace route, you'll see 16 because it's going to be in the trace route path, and we'll go all the way through what that looks like. But when the FRR kicks in, you will see 17 get put on, and then another label, and then the VPN service label, right? Because what's going to happen is you can't break that labeling. So when you do FRR, it actually puts another label on top so it can go the other direction. But then when it sends it to the merge point, it sends it as if the original LSP was on top of it. The original label was on it, right? Because when router 16 or router 7 gets it, if it's a different label, it will cause confusion. So you have to basically put a label on top, push another label on there. So you're going to see 3 labels instead of 2 normally. You'll see 3 labels. Once it gets to 5, 5 will, you know, push the label or put the label, take that label off and send it to router 7. Router 7 will just act like, hey, I got this from router 4. It'll look like to router 7 like I got it from router 4 because the next label would be the label that it just normally see. And then from that label, it will send to the correct uh, egress point. Now, that doesn't make any sense, but when you see it, then it makes sense. Okay. So now, first things first, we saw all of this stuff, right? So the first thing we're going to do, I'm running OSPF. So you see OSPF uh, inter area, right? Because I'm redistributing from BGP into OSPF. So I'm running MPLS L3 VPNs. You know you're going to see that as a OA unless you do something called a sham link. That's a totally different topic, so we're not going to talk about that. But you can see that I see router 9's loop back in my routing table. So I should be able to ping that from my loop back. Perfectly fine. So now let's look at the trace route. Excuse me. Hopefully that wasn't too loud. Let's look at the trace route. Now this is on the original path. Now again, based on my traffic engineering tunnel, it should go from router 1 to router 4, from router 4 to router 7 to router 7 to router 2. So now it's hitting router 1. Okay, so we're going to router 4. Okay, so that's router 7. That's labeled 17. Okay, so that router 7, because you see it went through that 10.1.4, and then it got to router 2, and it popped out on the other end. So the labeling is probably going to change because when I originally did this, it was 16. So okay, so now it's 17. So that's fine. We'll just say it's 17 for now. Now I'm going to bring down this link, and this is when FRR should kick in. But it does take some time because it's an even G thing. Okay, boom. Now recognize a link is down. In real life, it would recognize it immediately. But like I said, this is an even G thing. So now, when we run our trace route, let's see what happens. So when it gets to router 4, you should see 3 labels because it's going to go to router 5, then it's going to go to router 7, then it's going to go to router 2. So that's router 1. That's router 4. That's going to router 4. So you see it says 18, just like the one at the top. Now this one should see 3 labels. 17, 17, 28. And then you're going to see 2 labels again because now I got to the midpoint, which is this router here. It went this way, and then we were back at the midpoint. Then it's 28, which is going to router 2. And then back to, router 9. So this is what the FRR did. So basically what happened, and this is why I said when you see it, it makes more sense than me explaining it and just saying, okay, that's how it's supposed to go. So in the original trace route, we went to router 4, right? And then router 4 went to router 7 and got the label. So basically the remote label was 17, right? So it sent it with that label 17 on top, the top label. Then it popped off the top label. That was the PHP process. So it left you with the service label. And then it went to its respective router and got to, you know, 10, 255, 255.9. So what happens when we did the FRR, when a break happened and we had to have the backup LSP activate? So we still went to router 4. But when we got to router 4, this third label was sent from router 5. So it said, hey, I'm going to give you another label called 17. Now, this is where labeling your labels, like your label range, would work for you because this can cause confusion. But what I was telling you is this label 17 is basically saying, hey, your backup LSP is going to kick in and I'm sending you a label, a remote label of 17. So what I did was I put label 17 on there to go to router 5. But the original LSP label, the original, this right here, 1728, still needs to be attached because once I pop off 17, the top label of 17 that's coming from router 5, router 7 still has to get a label with the top label of 17 on it. It can't get a label of 28 because that's a service label, doesn't know anything about it. So 17 still has to get this label of 17 on it. Or router 7 still has to get the label of 17 on it. If I were to send it, go back to here. If I was to send it to router 5 and router 5 sent it with label 28, well then router 7 would say, I don't even have a reference point for router 28. So it would drop the traffic. So it's looking for 17. And that's why I said when you do the backup LSP, it has to look like it's still coming from the original path because that's the label I'm looking for, right? I'm looking for something with label 17. If you send me with something different, I am going to not recognize what that label is because I don't have it and I'm going to drop the traffic. So technically what router 5 did, let's hop into router 5 real quick. So what router 5 did was it sent a label to 17 to to router 4. You see that? Now the genius about this is it tells you what the next hop is going to take. So it says right here, I'm going to go to 10181, which is right here. All right. So router 5 sent router 4, hey, on your backup LSP, put 17 on top of it. But send me your original, right? Send me 1728, but actually, and then put another 17 on top of it so I know where to send this packet to. Okay. So router 5 got the 17, took off the 17, sent 1728, that original LSP labeling, to router 7, and then router 7 said, oh, I know what that looks like because I'm looking for 17 as my top label. You just sent me 17. So I now know I have to send the VPN service label on my original LSP that was created. Router 7 has no idea, doesn't really care. As long as it got the top label of 17, it can continue to function. If it got anything else, it would break. So now, and let's go to router 4. And we'll do that same command there, show IP RSVP fast reroute. So now you see the backup LSP is active, right? And again, it tells you the tunnel 0, label 17. That's say go to router 5. Okay. So now let's re-enable this. And we'll wait for a couple seconds. Now this came, I don't really care about router 7 anymore. We're going to wait a couple seconds. We don't care about router 5. We really don't care about router 1 anymore either. So now the adjacency is up, everything's good to go. Now the backup LSP should go back to backup or ready mode. As you can see, it's back to ready, but Look at the difference. See what the label changed this time. Now it's 16. Okay. So if we went to router 5, everything's working perfectly fine. All right. Everything's there. So as you can see, if I got 16, I would send it, if I was going that way, like let's say I sent it to 16 for some odd reason. I sent it to 16, I would go this way. But because I'm using that explicit path option, I'm never going to send the traffic to router 5 on that tunnel. So now we go back to router 15 and we want to run more trace route. It should look like the original trace route, which is the 18, 28. 28 is the service label. Then it should be 17, 28, then 28, and pops off the, well, when it gets to 28, it'll pop off the service label IP packet. But the PHP process is happening right here. So on router 4. Well, technically router 7. Let me not say router 4. Now the labeling changed, but the path is still going the way it's supposed to go. And that's the real tricky part about RSVP and MPLS TE. The labeling can change on you because you saw the original. In the original, it was 18, 17, 28, all right? But this time it's 16, 16, and then 28. And again, for you, the next question that's probably somebody's going to ask me is why is the numbers the same? Here's the thing, the numbering can be the same, but they mean totally different things per router, right? They don't necessarily, 16 on router 1 doesn't mean 16 on router 2. Okay, that's why I usually when I do MLD not MLDP, I'm about to say MLDP. When I do LDP stuff, I usually, and I'm not using LDP here, but when I usually do LDP based MPLS VPNs, I adjust the range so I know what router it is, right? So I don't get this because you see 16 and 16. If you're not aware that 16 can mean something totally different, then it could cause confusion. But if you have, okay, I have a range of 700 to 799, I know that's router 7, stuff like that. But that is MPLS TE in a nutshell. Now I'm going to give you one more little thing here, or WireShark it, because before I always want to WireShark before, so you guys can see it, what it looks like at a deeper level. Always WireShark, don't just lab to lab for understanding. So that means you may have to do some WireSharking to see how it looks at the packet level. Now we should see some path messages in here. There we go. Here's an RSVP. This is a reserved message. I'm looking for a path message though. Yeah, see, this is your reserved message. Here we go. Here's a path message. So here's the path message. And as you can see, expand this a little bit more. Here's my explicit path right here. This is the same thing that I configured at the tunnel. See that? Same way. When I showed you that show MPLS Traffic Engineering tunnel, this is what it looks like in WireShark. This is why I keep telling you guys, don't just lab to lab to understand, and definitely get WireShark in there so you can see what it looks like at the packet level, like what's in the packet. All right, here's your LSP destination, going to router 2. Here's the RSVP header that tells you it's a path message. And let's just do RSVP and router. Here we go. Let's stop right here. Here's your path message stuff. Here's your reserve messages on the way back, right? And then there you go. See the label? Label 16, sorry. Here's the label right here. So this is on the way back. Remember, when the reserve message comes back, it creates the label. And like I said, this is the reserve message, and here's the label. You didn't see that in the path message, right? You didn't see a label in the path message like I told you in the last video. So that's what it looks like at a packet WireShark level. Again, that is MPLS TE in a nutshell. Very basic. You can get really crazy with MPLS TE. I haven't even gotten to like forwarding adjacencies or any of that kind of stuff because those are more like advanced topics for MPLS TE. Now, if you're a service provider person, you should know about MPLS TE, forwarding adjacencies, next hop versus next hop, backup LSPs, all that good stuff if you're in the service provider track. But if you're in like, just regular enterprise stuff, you probably don't know anything about this because they don't teach you this. So this is Don from Padlock Technologies again. I hoped you enjoyed this video. It was very long, but because someone asked me to elaborate on MPLS TE, I feel like I would did you a disservice if I just showed you it and said, oh, this is how it works. All right. So this is Don from Padlock Technologies again. Hope you enjoyed this video. If you already subscribed, thank you. If you liked it, thank you. If you haven't, please don't forget to share, comment, like, and subscribe. Hope you enjoyed the video. Thank you, and have a nice day.